Greetings, students. Today, we embark on a fascinating exploration of a compelling challenge from LeetCode, problem 424, titled Longest Repeating Character Replacement. This problem invites us to delve into the intricacies of string manipulation. It asks us to determine the maximum length of a contiguous substring that can be formed by replacing at most k characters in a given string consisting solely of uppercase letters. Consider the example presented. If we have the string AA bay and are permitted to make one character replacement, we can convert one B into an A, thereby crafting the substring AAA with a remarkable length of 4. Our objective is to ascertain this maximum length after performing the allowable character transformations. As we dissect this problem further, let us appreciate the elegant interplay between string theory and algorithmic efficiency. The sliding window technique is a powerful algorithmic tool used to solve problems involving sequences or arrays. Imagine you're looking at a long row of houses, and you want to find the best view from a specific segment of that row. The window represents the segment you're examining. It can expand or contract based on what you find, allowing you to focus on just the relevant houses without having to check each one multiple times. This technique is particularly useful when time efficiency is crucial. By using a sliding window, we can often transform a problem that might take quadratic time, like checking every possible combination, into one that runs in linear time. This is essential for larger data sets, as it keeps our solutions feasible. At its core, the sliding window technique uses 2 pointers to mark the start and end of our window. We begin with both pointers at the start and move through the dataset, adjusting them as needed based on specific conditions. This dynamic adjustment helps us systematically explore different sections of the data while keeping track of what we need, leading us to the best solution. In this slide, we're looking at a function that calculates the sum of every k consecutive elements in a list using the sliding window technique. First, we initialize our variables. The window sum holds the sum of the first k elements. This is our starting point, and we store this initial sum in the result list. Think of this as forming a small group of elements from our list, which we will analyze together. Next, we slide our window across the array. For each new element we encounter, we update our window sum by adding the new element and subtracting the element that is now outside our window. This keeps our calculations efficient, avoiding the need to sum all k elements from scratch each time. Finally, we return the result, which now contains the sums of all these windows. This technique is powerful because it allows us to maintain a running total efficiently, making it ideal for problems involving sequences or continuous data. A frequency array with a size of 26 is a powerful tool used to count how many times each lowercase English letter appears in a string. Think of it like a box with 26 compartments, where each compartment is labeled with a letter from A to Z. When we encounter a character in our string, we simply go to the corresponding compartment and increase the count by 1. This method is incredibly efficient. By using a fixed size array, we can quickly tally character occurrences with just one pass through the string, achieving a time complexity of O(n), where n is the length of the string. Once we've filled our frequency array, we can easily determine the most common letter or check if a specific letter exists, all in constant time. Understanding how to implement and utilize frequency arrays is crucial for various tasks in string processing, such as frequency analysis or solving problems related to character distribution. This compact approach not only simplifies our code, but also enhances our performance when handling large datasets. Let's dive into the concept of a frequency array, particularly for processing lowercase letters in a string. In this function, we start by initializing a frequency array with a size of 26, which corresponds to the 26 letters in the English alphabet. Each index in this array represents a letter, where index 0 is A, index 1 is B, and so on, up to index 25 for Z. Next, we process each character in the input string. If the character is a lowercase letter, we find its index by subtracting the ASCII value of A from the ASCII value of the character. This calculation gives us the exact position in our frequency array. We then increment the count at that index to keep track of how many times each letter appears. Finally, we return the completed frequency array. For example, when we input the string hello, The output array shows how many times each letter appears, with numbers indicating the frequency. In this case, H appears once, E once, and L twice, while all other letters have a count of 0. Understanding this frequency array is crucial for solving the longest repeating character replacement problem effectively. The two-pointers approach is a powerful technique in algorithm design that uses two distinct pointers to traverse a data structure, like an array or a linked list. Imagine you're at a race, with one runner starting at the beginning and the other at the end. As they move towards each other, they can efficiently compare their positions and make decisions based on what they find. This method is particularly useful for problems that involve searching, sorting, or merging data. For instance, if you want to find pairs of numbers that add up to a specific value, using two pointers can help you streamline the process. Instead of checking every possible pair, you can systematically eliminate options, reducing the time complexity from O(n) toer with a nested loop to a much more efficient O(n). At a high level, you start by initializing two pointers at specific indices, often at the start and end of an array. As you compare the values they point to, you move them closer together based on certain conditions. This continues until they meet or cross, allowing you to explore the dataset efficiently without unnecessary comparisons. This is why the two-pointers approach is not just intuitive, but also a crucial tool for solving complex problems effectively. The two-pointer approach is a powerful technique for solving problems involving sorted lists. Here, we explore the function two-pointer sum, which identifies unique pairs in a sorted list that sum to a specific target. First, we initialize two pointers. Left starts at the beginning of the list, and right is positioned at the end. This setup allows us to efficiently explore potential pairs. As we loop through the list, we calculate the sum of the values at these two pointers. If this sum matches our target, we've found a valid pair, which we then store. Next, we adjust both pointers, moving the left pointer to the right and the right pointer to the left, ensuring we don't revisit pairs. If the current sum is less than the target, we move the left pointer right to increase the sum. Conversely, if it's greater, we move the right pointer left to decrease the sum. This method effectively narrows down our search, ensuring we find all unique pairs efficiently. Finally, we return the collected pairs. This illustrates how the two-pointer technique can simplify finding solutions in sorted data. To solve the problem of finding the longest substring that can be formed by replacing at most k characters in a given string S, we'll use a systematic approach. First, we initialize some key variables. We need a max count to track the most frequent character in our current window, and a count map, which is a dictionary to record how many times each character appears. We also set two pointers, left and right, both starting at the beginning of the string, to define our current window. Next, we will expand our window by moving the right pointer through the string. As we add characters, we update our count map and adjust max count to reflect the highest frequency of any character in our current window. Now we need to ensure our window stays valid. We check if the number of characters that need replacing exceeds k. If it does, we increment the left pointer to shrink the window until it's valid again, updating our count map as we go. After adjusting, we keep track of the maximum length of valid windows we've encountered. Once the right pointer has traversed the entire string, we return this maximum length. This algorithm efficiently runs in O(n) time, as each character is processed at most twice, making it both effective and practical for our needs. In this problem, we are tasked with finding the length of the longest substring consisting of repeating letters in a given string, after performing at most k character replacements. The string is exclusively composed of uppercase English letters, and its length can range from 1 to 100,000. Notably, the number of allowed replacements, k, must be between 0 and the length of the string itself. These constraints guide our approach to efficiently solve the problem while considering the potential scale of the input. The provided Python code addresses LeetCode problem 424, which asks us to find the length of the longest substring we can create by replacing at most k characters in a string S. To tackle this problem efficiently, we use a technique called the sliding window. We start by setting up two pointers, left and right, to mark the edges of our current window in the string. The variable maxCount tracks the frequency of the most common character in this window. Meanwhile, we maintain a list called count to keep track of how often each character appears, indexed by their ASCII values. As we move the right pointer through the string, we increment the count for the character at sRight. We then update maxCount to ensure it reflects the highest frequency of any character in that window. Next, we check if the total number of characters in our window, minus maxCount, exceeds k. If it does, we need to reduce the window size by moving the left pointer to the right, which effectively shrinks our window from the left. Finally, the length of the largest valid window is calculated as len(s) minus left. This sliding window approach is optimal, running in O(n) time complexity, where n represents the length of the string. This efficiency comes from the linear traversal and the limited operations needed on our frequency array. The time complexity of the longest repeating character replacement algorithm is O(n). This means it processes the input string in one complete pass, where n represents the length of that string. Think of it like reading a book. You don't stop to reread each word, you simply go from the beginning to the end, keeping track of important details as you go. In this case, the algorithm counts characters and checks conditions in constant time for each character, leading to that linear time complexity. Now let's talk about space complexity, which is O(1). This is a bit different. Imagine you're packing for a trip and you only need a small suitcase, no matter how long your trip is. The algorithm uses a fixed amount of space for variables, like counts and pointers, that doesn't change with the size of the input string. This means that no matter how long the string is, the space it requires remains constant, which is quite efficient. Understanding these complexities helps us appreciate how algorithms can be both time efficient and space efficient.